Welcome to Night Chemistry, your midnight laboratory of calm. Tonight we voyage with oxygen, element 8, the breath behind every ember and the quiet partner in each heartbeat. Over the next 2 hours we will follow oxygen from fiery birth inside ancient stars to Joseph Priestley's glowing bell jar, then through green leaves at dawn and into the faint blue halo that guards our planet. Let the pace slow to 60 beats per minute, the tempo of restful hearts. Close your eyes or soften your gaze. Feel the day's weight slide away. All you need to do is breathe in, breathe out, and drift on the element that sustains life. Settling into elemental calm. 0.1. Guided 446 breath. Rest one hand lightly on your abdomen. Sense the gentle rise and fall. Inhale through the nose to the count of 1, 2, 3, 4. Hold that breath, chest comfortably full. 1, 2, 3, 4. Exhale in a smooth, unbroken stream. 6, 5, 4, 3, 2, 1. Again. Inhale. Cool air glides downward toward the diaphragm. Hold. Notice a quiet pause between heartbeats. Exhale. Let the shoulders soften as air leaves. Repeat the cycle once more at your own tempo. Each inhale gathers composure. Each pause offers stillness. Each extended exhale washes tension away. When the rhythm feels effortless, allow breathing to settle into its natural pattern. The 446 cadence will remain as a gentle undercurrent. 0.2. Element-specific visualization. Imagine first light cresting a quiet forest. Gray trunks stand in orderly silence, their crowns hidden by morning mist. That mist is cool and faintly sweet. It carries 21% oxygen, just enough to wake a robin, kindle a campfire, or quicken a runner's stride. Step into the scene. Damp leaves cushion each footfall. With every breath the lungs fill with misty air. Deliver oxygen to blood, and send it to muscles that relax a fraction more. Above the treetops sunlight touches the fog. Photons strike chlorophyll and prompt the first molecules of oxygen to leave green cells, gifts from night's photosynthesis. Those newborn O2 pairs drift downward like invisible snow, joining the atmosphere's ancient reservoir. Turn toward a small clearing where someone has built a stone ring around a single pine log. A match flares. The flame is small, amber, almost bashful. It leans into a breath of fresh air and leaps taller, its color brightening to white. That brightness is oxygen accepting carbon's embrace, releasing light and warmth in gratitude. Watch the fire grow steady, not roaring, just enough to toast dawn. Shift focus to the surface of a quiet pond nearby. Early rays slide across mirror-smooth water. Beneath that surface microscopic bubbles cling to curling pondweed leaves. Each bubble is pure oxygen produced moments ago by submerged stems. Tiny fish weave among the bubbles, nipping at algae, their gills fluttering in the concentrated gift. Now raise your gaze to the sky. The faintest azure tint unfurls overhead, deepening from pale powder to strong cerulean. That color is Rayleigh scattering intensified by oxygen's polarizability. Higher still, unseen ultraviolet rays split pairs of O2, which recombine as 3-atom ozone. A fragile shield forms, guarding skin and seedlings below from solar flame. Back on the forest floor, inhale slowly. Taste a hint of pine resin and distant wood smoke. Hold the air for 4 counts. Exhale longer than you inhaled. And imagine exhaling gentle carbon dioxide that rises to branches eager for sunrise sugar. You and the forest trade gases with perfect courtesy, neither giving nor taking too much. Feel your body settle. Shoulders drop toward the mattress or earth. Fingers uncurl. The jaw loosens. Pulse moves unhurried beneath the palm resting on the abdomen. Breathing now sounds like a soft tide within a sheltered cove. One more conscious cycle. Inhale 4. Breathe in clear woodland air. Hold 4. Sense stillness gathering at the center. Exhale 6. Let warmth flow outward, tension flowing with it. You are ready. The element that supports life stands beside you, bright in flame, silent in mist, blue in sky, and steady in every pulse of blood. Our journey into oxygen's discovery, properties, and cosmic travels begins. Breathe easy and follow the flame. Discovery 1.1. Who discovered oxygen? Our story of discovery flows through three minds separated by distance yet linked by curiosity. Carl Wilhelm Scheele, a Swedish apothecary, first extracted the element in 1771 while heating mercuric oxide and potassium nitrate inside thick glass retorts. In his modest pharmacy at Köping, he labeled the unfamiliar gas fire-air. It brightened embers with startling energy and kept a mouse alive far longer than common air. Scheele wrote careful notes but delayed publication, thinking he should test more substances before announcing results. Joseph Priestley, minister and natural philosopher in Leeds, met the element 3 years later. On the first day of August 1774, he focused sunlight through a burning lens onto a bit of red mercuric oxide sheltered beneath an inverted glass bell resting over liquid mercury. A clear gas formed, displaced the metal, and gathered under the bell. When he introduced a glowing splinter, it burst into brilliant flame. Placing a mouse inside, he observed it thrive, as if the new air were 5 or 6 times better than common air. Priestley called it dephlogisticated air in the language of his day, believing it lacked phlogiston, the hypothetical substance of fire. Across the Channel, Antoine Laurent Lavoisier, a Parisian savant and meticulous tax officer, performed parallel work in 1775. Hearing accounts from Priestley and from Scottish chemist Daniel Rutherford, he repeated the red calx experiment but framed it through weight and balance. Lavoisier weighed the calx before and after heating, weighed the escaping gas, and found that the mass missing from solid appeared in the gaseous product. He concluded that combustion did not release phlogiston but rather absorbed a component of air, and that red calx released this component when decomposed. He forged a bold claim. The new gas was a distinct element essential for combustion and for respiration. Each researcher shone a lamp on a single face of oxygen's identity. Scheele isolated it earliest. Priestley demonstrated its remarkable properties to the Royal Society, and Lavoisier named and explained it within a new chemical language. The trio stands together at the gates of modern chemistry, ushering in an age where careful measurement eclipsed inherited doctrine. 1.2. When oxygen was discovered. Picture the 1870s, a decade of overlapping revelations. 1771. 1772. Scheele records in his notebook that heating manganese dioxide with concentrated sulfuric acid or calcining mercuric oxide produces a pure gas that makes a candle burn strongly. He writes to Lavoisier but delays printing. A 1st of August, 1774. Priestley performs his lens experiment in a small stone outbuilding behind Bowood House, Wiltshire. He notes that mice flourish, a candle blazes, and the air tastes peculiarly agreeable. That autumn he travels to Paris, shares samples with Lavoisier, and describes the method. February 1775. Lavoisier heats lead and tin calxes in closed vessels, collects the same gas, and publishes Memoire sur la nature de l'archaiste absorbe par les substances métalliques. He does not yet name the gas but announces that combustion absorbs part of the atmosphere. A 1777. Scheele finally sends his manuscript Chemische Abhandlung von der Luft und dem Feuer to the Academy in Stockholm. Wartime delays postponed printing until 1779, 2 years after Lavoisier's decisive paper. 1783. In Methode de nomenclature chimique, Lavoisier and colleagues coined the word oxygen, meaning acid former, believing the gas essential to every acid. Though the acid theory later fades, the name remains. English chemists adopt oxygen by 1787. In the span of little more than a decade, A colorless gas hidden within red mineral powders travels from obscure notebooks to the beating heart of scientific revolution. By the time the French Revolution ignites, oxygen has overthrown phlogiston and established quantitative chemistry as the new authority. 1.3. Conditions and circumstances of discovery. Scheele's pharmacy laboratory. Imagine shelves crowded with earthenware jars, each labeled in neat copperplate. Calx of lead, flowers of sulfur, vitriolic spirit. A brick hearth glows. Over it hangs a small glass retort sealed by waxed linen string. Scheele works mostly alone, sniffing vapors to identify them, trusting his sharp senses. Coping's winter winds howl outside, yet inside the air warms and thickens with sulfurous fumes. Lacking sophisticated pumps, Scheele uses water displacement and oiled leather bladders to capture his gases. He identifies fire-air by its hunger for flame and by its sweet freshness on his breath, but he still embraces phlogiston, believing his fire-air absorbs phlogiston more readily than common air. Priestley's garden shed and bowwood attic. Travel to rural Wiltshire. Behind a stately manor stands a modest shed. Sunlight funnels through a large burning lens, 2 glass hemispheres filled with water, mounted on an iron frame salvaged from a lantern projector. The lens concentrates the August sun onto a china cup holding red mercuric oxide. Inside a bell jar resting over a mercury trough, the calx glows orange. Transparent bubbles rise. Priestley, ever the meticulous diarist, writes by the shed's dim window. The air within appears no heavier. A candle placed therein burns with a dazzling flame. He lowers a small white mouse in a wire cage, notes its lively grooming 30 minutes later. He arrays candles of equal length, one in common air, another in the new air, and measures how much longer the latter burns. In sermons he will later draw moral lessons from the purity of dephlogisticated air. Lavoisier's Hotel Particulier on Rue de la Contrescarpe. Step into a high-ceilinged salon converted into a laboratory with mahogany benches, brass balances capable of weighing to the 1,000th of a grain, and rows of sparkling glassware. Assistants stoke charcoal in a wind-regulated furnace. Lavoisier, wearing a lace cuff pulled back from his wrists, weighs mercuric oxide before heating and again after red powder turns to shining beads of mercury. He collects the evolved gas over mercury rather than water to avoid dissolution. He notes volume, pressure, temperature, and precise mass changes. A clerk writes figures. Madame Lavoisier sketches the apparatus in ink wash. The scene embodies Enlightenment ideals. Reason, precision, collaboration. Lavoisier's study ends with a bold sentence. La combustion est donc l'union d'un corps avec cette partie de l'air que j'appelle oxygen. Combustion is union, not release. Phlogiston false. In Lutheran Germany, Anglican England, and Catholic France, most chemists still teach phlogiston. Substances burn, releasing an invisible principle of fire. Weight paradoxes accumulate. Metals gain mass when calcined, yet theory says they should lose. Priestley tries to defend phlogiston by suggesting it may possess negative mass. Lavoisier instead abandons phlogiston, aligning his results with conservation of mass. In 1783 he publicly debates advocates of the old theory at the Academy, using oxygen data as decisive blow. The Enlightenment now has its flagship element, oxygen, embodying the victory of measurement over speculation. Instruments and hazards. All three pioneers rely on simple gear. Retorts, bell jars, mercury troughs. Mercury serves twice. It seals joints and displaces water that would dissolve gases. Poisonous vapor fills the air, though none yet realize the dangers. Phosphorus matches glow bright, yet fumes sear lungs. They work without goggles, gloves, or fume hoods, guided by curiosity alone. In their journals words like noxious, acrimonious, and sweet describe smells tasted directly. Yet out of such risk emerges the knowledge that our every breath is a partnership between body and an element hidden in red powder. Correspondence and community. Letters cross borders by carriage and packet boat. Priestley posts samples of dephlogisticated air in sealed files to Paris. Lavoisier shares weight tables. Sheely reads translations months late but recognizes his own fire air in others' reports. The Royal Society's philosophical transactions and the Academy's memoirs carry diagrams of bell jars and retorts, inviting replication. Discovery no longer hides in princely courts. It travels through coffee houses, dissenting chapels, and village pharmacies. Oxygen's revelation becomes an early experiment in open science. The broader world. Beyond laboratories, lightning still splits air. Sailors still burn tallow lamps in calm tropic seas. Miners still struggle for breath. Yet within 2 decades, pneumatic chemistry yields bottled medical oxygen for treating collapsed lungs, calcium hypochlorite bleach for whitening linens, and oxyhydrogen blasts hot enough to fuse platinum. The practical consequences spread quickly. A single element discovered in red powder starts to reshape industry, medicine, even laundry. Pause for a breath. Inhale to a calm count of 4, hold 4, exhale 6. As you release, imagine yourself setting down a quill beside Joseph Priestley's final note of the day. The candle in his study burns white and fierce, fed by a sample of pure oxygen. Its steady flame mirrors the new clarity of thought that oxygen has brought to science. The element is no longer hidden. From Coping's pharmacy, Priestley's shed, and Lavoisier's grand salon, oxygen steps into the world. Next we will explore its nature. Why it is paramagnetic, why it chills to blue liquid at -183 Celsius, and how it shapes blue sky and ozone shield. For now rest in the glow of that bowwood bell jar, the tiny mouse alive and well inside, breathing the element that will soon light cities, forge steel, and carry life across generations. Take one more unhurried breath. Feel lungs expand, hemoglobin embrace oxygen, cells receive a midnight gift. Exhale and let the mind drift, as softly as mercuric oxide once crumbled into shining drops and released a gas that changed the world. Properties and presence. 2.1. Key physical and chemical properties of oxygen. Take a slow breath. The air that enters is almost 1/4 oxygen, yet it feels weightless. That paradox, profound effect masked by gentle presence, defines the element. Bonding temperament. In its everyday form, oxygen appears as O2, two atoms joined by a double bond. The outer orbitals hold 6 valence electrons, leaving 2 unpaired. Those lone electrons grant oxygen high electronegativity, 3.4 on the Pauling scale, second only to fluorine. Because of that pull, oxygen tugs electrons from almost every element it meets, driving combustion, rust, cellular respiration, and stone weathering. Spin and magnetism. Unlike most diatomic molecules, O2 exists in a triplet ground state. The lone electrons keep their spins parallel. That alignment makes oxygen paramagnetic. Place liquid oxygen between the poles of a strong magnet and the pale blue stream bends inward like water pulled by invisible lunar tide. In 19th century France, Louis Paul Cailletet first noticed the effect when droplets of condensed oxygen clung to a magnet's tip, an early hint that quantum rules guide even colorless gases. Color and phase changes. Gas phase oxygen is clear, but condense it at -183 degrees Celsius and it becomes a blue liquid deeper than alpine ice. Cool further to -219 degrees Celsius, and it freezes into brittle, translucent crystals with a faint aqua tint. The color comes from electronic transitions forbidden in most molecules but allowed in O2 because of its unpaired spins. Shine white light through a centimeter of liquid oxygen and it emerges robin egg blue, a quiet beauty hidden inside hospital cylinders. Allotropes. Add energy, spark, electric field or ultraviolet ray. And some O2 splits, then rejoins as O3 ozone. Ozone bends into a triangular molecule that absorbs ultraviolet C and ultraviolet B, shielding DNA of leaf, lizard, and lung. At ground level, however, ozone irritates mucous membranes. The same reactivity that blocks solar radiation also scratches respiratory tissue. Form and context decide whether oxygen heals or harms. Beyond ozone lies a rarer form. Singlet oxygen, O2 with paired spins raised into an excited electronic state. In rose petals, singlet oxygen fades pigments. In dermatology clinics, doctors harness it in photodynamic therapy to destroy tumors. Life learned to build enzymes such as superoxide dismutase and catalase precisely to tame these reactive offspring of ordinary oxygen. Electronic footprints. Spectroscopists love oxygen's fingerprint bands. The 0 to 1 atmospheric band near 760 nanometers marks O2 in exoplanet atmospheres. The millimeter wave O superscript 1 fingerprint lets climate scientists study past rainfall trapped in polar ice. Even a single isotope switch from O16 to O18 shifts vibrational frequencies just enough to reveal ancient monsoon rhythms. Energetics. When carbon meets oxygen in full combustion, each gram of carbon releases 32 kilojoules. Rocket engines feed kerosene or liquid hydrogen with liquid oxygen because no other common oxidizer releases so much energy so cleanly. In mitochondria, enzymes harvest that energy not in flame but in 30 tiny proton pumping steps, converting it to adenosine triphosphate instead of heat. Oxygen's gift is generous. Biology learned to unwrap it carefully. Pause here. Inhale 4 counts, hold 4, exhale 6. Feel cellular turbines spinning silently, turning oxygen's pull into pulse and thought. 2.2. Oxygen in the periodic table. Visualize the periodic table as a great mosaic of colored tiles. Navigate to period 2, the second row where atomic radii remain small and bonds grow tight. Move to group 16, also called the chalcogens. There sits the tile labeled O, atomic number 8, mass 16. Neighborhood influences. To oxygen's left stands nitrogen, moderate in pull, content with sharing. To the right lurks fluorine, the ruthless electron thief. Oxygen balances between them. strong enough to drive rust, gentle enough to coexist with life. The rest of Group 16 shows a slide from airy non-metal to silvery metal. Sulfur, selenium, tellurium, and polonium step downward in atomic weight, softening electronegativity, embracing metallic shine. Oxygen crowns the column as lightest and most reactive, yet paradoxically the least metallic. Electron configuration. 1s orbital holds 2 electrons, followed by a full 2s pair, and 4 electrons in 2p orbitals. 2 paired, 2 unpaired. That half-filled p shell explains oxygen's double valence. It usually forms 2 bonds, as in H2O, CO and O2. Yet it flexes into 4 coordinate structures when dative bonding or high oxidation states beckon, as in perchlorate or phosphate, where oxygen plays anchor rather than protagonist. Ionization and affinity. High first ionization energy means removing an electron costs oxygen dearly. Instead, it prefers to gain or share. High electron affinity means oxygen greedily snaps up spare electrons from sodium, magnesium, and aluminium, forming oxides that coat metals in protective patina, or corrode them completely if moisture joins. Engineers develop paints, passivation films, and stainless alloys to dance with this relentless appetite. Periodic trends. Cross the row from lithium to neon and atomic size shrinks while electronegativity rises. Oxygen sits near the apex of that rise, 1 step shy of fluorine, making it the keystone oxidizer of planetary surfaces. Without oxygen's place on that ridge, Earth might mirror the rust-free basalt deserts of Mars before its brief oxidizing episode. Chemistry, geology, and biology hinge on that single square. Take another breath. The lungs do not parse periodic tables, yet they intuitively bow to that square each second, handing venous blood to alveolar sacs in trust that oxygen will make the trade silicon never could. 2.3. Prevalence and natural sources in nature. Atmosphere. Open a window, real or imagined. Soft wind arrives carrying roughly 21% oxygen, nitrogen the backdrop, argon the whisper. That proportion rose from less than 1% in the Archean Eon to 35% during the Carboniferous when dragonflies spanned 70 centimeters. Today's 21 strikes a balance. Enough to feed metabolism, not so much that lightning ignites forests with every strike. Photosynthesis maintains it. Respiration, fire, and rock weathering draw it down. The two fluxes meet in silent algebra, and Earth's sky stays blue. Hydrosphere. Cold oceans dissolve more O2 than warm. Antarctic seas approach 400 micromoles per kilogram, fueling krill blooms that feed penguin parades. In tropical shallows, oxygen slips away by midday as photosynthesis and respiration chase each other. Corals rely on wave action to replenish O2. Stagnant lagoons turn hypoxic. Scuba divers watch gauges not for nitrogen narcosis first but for partial pressure of oxygen. Too little brings blackout. Too much at depth convulses nerves. Water teaches oxygen's Goldilocks lesson more vividly than air. Lithosphere. Count atoms in granite and basalt, and you discover that 46% of Earth's crust by mass is oxygen. It combines with silicon to make quartz and feldspar, with iron to make magnetite, with aluminium to form bauxite. Even gemstones, ruby, sapphire, emerald, are aluminium or beryllium oxides tinted by trace metals. Dig anywhere and you hold a story of oxygen frozen into lattice. Beneath crust lies mantle rich in magnesium silicate perovskite, again dominated by oxygen. At 400 kilometers depth, high pressure reshuffles atomic positions, but the element remains. Only in the liquid iron core does oxygen yield dominance to metallic realms. Yet spectroscopic hints suggest even the core holds a few percent oxygen dissolved within molten iron, a stowaway influencing seismic wave speeds. Biosphere. Every green leaf and cyanobacterial mat produces oxygen when photons split water molecules. The reaction liberates 4 protons, 4 electrons, and one O2 molecule for every 8 photons. Over billions of years, cyanobacteria pumped enough oxygen to rust oceans, stain riverbeds red with hematite, and eventually bleed into air. This great oxidation event 2.4 billion years ago killed most anaerobes, yet cleared a path for complex life that could harness the energy locked in aerobic respiration. Today, forests exhale about 45 gigatons of oxygen annually. Oceans add another 200 gigatons. Almost all is reabsorbed quickly by respiration and decay. The atmospheric reservoir represents just 3,000 years of net output, a fragile storehouse. Yet for 3 millennia and counting, the ledger balances, courtesy of sunlit leaves and shading plankton. Cosmos. At ultraviolet wavelengths, astronomers detect oxygen's fingerprint in nebulae such as the Orion Bar, where newborn stars photoionize O superscript 2, producing teal glows. In comets, ultraviolet sunlight dissociates water ice, releasing atomic oxygen that fluoresces green, a ghostly aura framing passing icebergs in space. Martian rovers measure 21,000 parts per million of oxygen in afternoon air, produced by photolysis of CO2. On Europa, Jupiter's radiation splits surface ice into hydrogen, lost to space, and trapped O2 bubbles. If a subsurface ocean exists, that oxygen may slowly trickle downward, offering a chemical handle for life. Exoplanet hunters search for the oxygen triple fingerprint, O2 at 760 nanometers, ozone at 9.6 microns, and water at 1.4 microns, as a potential sign of biology. Yet caution reigns. Non-living processes can mimic some signals. Even so, a planet bathed in free oxygen suggests something profound: energy harvested from a star and released back to space in chemical form. Pause once more. Inhale. Hold. Exhale. Imagine that the oxygen just entered may have risen from a kelp forest only days ago, or split off a Himalayan glacier centuries past, or drifted from Amazon leaves this morning. Elemental presence transcends time scales the way dreams transcend waking concerns. The element's nature now feels clearer. Blue cold, magnetic, voracious, in love with electrons, yet balanced in planetary cycles. It dominates rocks, whispers in oceans, and paints nebulae. As we turn next to oxygen's role in the wider universe, let breaths carry this knowledge deeper. Inhale 4 counts of cool night air. Envision each O2 pair rotating, translating, ready to serve in lungs, in flames, in distant comets. Hold, letting oxygen diffuse across alveolar membranes. Exhale 6, sending a softer mixture back toward the trees outside or the houseplants on a sill. Rest in this silence for a moment, aware of the living bond between starlight-split water and beating heart. Oxygen is there, steady and bright, awaiting the next chapter of our midnight exploration. Role in the universe. 3.1. How oxygen is forged in stars. Begin with a vision of a star 10 times heavier than the Sun. Deep in its core, gravity squeezes matter so fiercely that helium nuclei, the ash of earlier fusion, collide 3 at a time in the triple alpha process to make carbon-12. Soon temperatures climb past 100 million Kelvin, and a new reaction kindles. Carbon captures an alpha particle, forming oxygen-16 plus radiant energy. This step is the carbon-alpha cycle. Without it, no breathable air, no rust-red autumn, no quartz beaches would exist. The first of these oxygen-making stars flared and died long before Earth formed. When their helium fuel thinned, fusion shells shifted outward. In a red supergiant's swollen mantle, fresh oxygen mixed with neon, sodium, and magnesium. The giant then collapsed, rebounded, and exploded as a Type II supernova. Shock waves hurled oxygen into interstellar space at thousands of kilometers per second. Each grain of dust that later condensed carried a sprinkling of O16 atoms. Our own sun, smaller and steadier, will never reach internal temperatures high enough to fuse carbon into heavier elements, so it will leave carbon and oxygen locked in a white dwarf core. These dwarf remnants populate the Milky Way like silent embers, each an inert crystal of carbon and oxygen cooling for eons. Astronomers read oxygen's presence by spectral lines. In planetary nebulae, doubly ionized oxygen glows teal at 501 nanometers. That forbidden line paints graceful rings such as the Helix Nebula. In supernova remnants, neutral oxygen emits bright red at 630 nanometers. Through telescopes, these colors reveal where and when oxygen condensed from stellar furnaces into cosmic clouds. Take a slow breath. As you inhale, imagine those teal and scarlet signatures drifting across the universe, whispering that stars have been forging oxygen for 13 billion years so that lungs on a small blue planet could one day rely on it. 3.2. Oxygen's travels across galaxies and planetary worlds. After ejection, oxygen atoms ride an interstellar motorway of dust grains and icy mantles. In the cold of molecular clouds, they bond with hydrogen, forming water ice that coats silicate cores. When ultraviolet light from newborn stars breaks some bonds, reactive oxygen meets carbon monoxide, forming carbon dioxide frost that whitens comet nuclei. In the Orion molecular cloud, radio telescopes tune to 18-centimeter wavelengths to follow hydroxyl radicals, harbingers of water. Where OH intensifies, future solar systems gestate. Gravity gathers dust, ice, and gas into spinning disks. Inside these disks, oxygen adopts varied destinies. If in the inner hot zone, it oxidizes silicates, building olivine and pyroxene minerals that will become the rocky crusts of terrestrial planets. In the midzone, it teems with metals to fashion oxides of iron and aluminium, seeds for asteroid cores. Beyond the snowline, it freezes as water ice, bulking gas giant moons and comet reserves. Our own solar system still displays oxygen's versatility. Earth boasts 21% atmospheric O2 and an intangible triple oxygen shield. Ground level O2 for breathing, stratospheric O3 blocking ultraviolet, and high-altitude O atoms glowing green in auroras. Mars shows faint oxygen lines in sunset spectra. They arise from photolysis of CO2. When dust storms lift, surface rocks slowly oxidize, staining the landscape rusty. Yet free oxygen never gathers densely. Lacking trees and plankton, Mars cannot replenish what ultraviolet light strips away. Europa, Jupiter's icy moon, receives radiation that shatters surface H2O into hydrogen and oxygen. Hydrogen escapes, while oxygen bubbles migrate downward, perhaps dissolving in a subsurface sea. If microorganisms swim there, oxygen could feed metabolisms independent of sunlight. Titan bears a haze of organics above frigid methane lakes. Even here oxygen lurks. Trace O2 flows from Enceladus's plumes, captured by Titan's gravity, mixing with photochemical radicals to make carbonyl sulfide and formaldehyde snow. Farther out, on Neptune's moon Triton, sublimating nitrogen winds scour reddish patches. Spectral scans reveal carbon monoxide and carbon dioxide frosts containing oxygen delivered by comets. Across the Milky Way, giant molecular clouds glitter with infrared water vapor bands. Oxygen in supernova remnants cools gas, enabling cloud collapse. Astronomers measure O/Fe ratios in metal-poor halo stars, learning how successive stellar generations enriched galaxies. High O/Fe implies early massive stars dominated, forging abundant oxygen before longer-lived supernovae injected iron. On the scale of the cosmic web, oxygen's absorption lines in quasar light mark intergalactic filaments hundreds of millions of light-years long. Where hot gas cools on these filaments, O6 ions trace baryonic matter otherwise invisible. Oxygen becomes both cosmic thermostat and signpost. Inhale gently, picturing an oxygen atom emerging from a supernova shock front, drifting through nebular ice, spiraling into a comet, then flashing green in an aurora billions of years later. Exhale and let that timeline dissolve into the present room. 3.3. Planetary atmospheres, ozone shields, and exoplanet clues. Earth's sky did not always brim with O2. For its first 2 billion years, the atmosphere was reducing, rich in methane and ammonia. Then cyanobacteria mastered oxygenic photosynthesis, splitting water with sunlight and releasing oxygen as waste. Iron dissolved in ancient oceans captured O2, forming banded iron layers that miners quarry today. Only after those sinks filled did O2 accumulate in air, an epoch called the Great Oxidation Event. Oxygen levels rose again in the Devonian when land plants spread, each leaf a solar-powered water splitter. During the Carboniferous they peaked near 35%, letting dragonflies grow hand-wide wings. Modern 21% owes its balance to dueling processes. Photosynthesis raises O2, respiration and decay lower it, and geological burial of organic carbon locks oxygen in air. Lightning and ultraviolet convert some O2 to ozone, forming a tenuous stratospheric layer. Ozone filters DNA-damaging ultraviolet B, shaping evolution's pace. Volcanoes release sulfur dioxide and carbon monoxide that scavenge oxygen, but weathering of silicate rocks consumes CO2 and frees O2. Thus, a homeostatic loop emerges. Warmer climates accelerate weathering, drawing down CO2, cooling Earth, stabilizing O2. Ice ages slow weathering. Volcanic CO2 rebounds. Oxygen dips then recovers. Over millions of years, these seesaw motions average to the composition we breathe. Oxygen's signature reaches space. Satellites detect a night-side red glow at 630 nanometers, caused by atomic oxygen recombination. This airglow lights polar horizons in winter months, guiding research planes across dark ice fields. On other worlds, oxygen can arise without life. Ultraviolet photolysis of water on a planet orbiting a dim red dwarf may split H2O, letting lighter hydrogen escape to space and leaving oxygen behind, a process called abiotic O2 buildup. For astrobiologists, detecting O2 alone is not a smoking gun. They seek the triple fingerprint: abundant O2, a modest ozone band, and reduced gases such as methane present simultaneously. Life tends to maintain such disequilibria. Geology rarely does. Upcoming missions like the James Webb Space Telescope and the Large UV Optical Infrared Surveyor aim to study Earth-sized exoplanets around Sun-like stars, looking for the oxygen triplet. A future spectrum showing all three bands could signal photosynthesis on a distant continent, waving chemical hello across interstellar darkness. Within our solar system, the closest analog to early Earth stands on Mars. The ExoMars rover will drill for perchlorate-bound organics and measure isotopic ratios of oxygen in sulfates. Variations could reveal whether transient liquid water once cycled oxygen through biological pathways. At the same time, NASA's Europa Clipper will sniff oxygen plumes over Jovian seas, searching for trace organics that ride alongside. Pause once more. Inhale for 4 counts, hold, exhale for 6. Feel air past the lips, imagine its journey traced on a cosmic map. Born in fusion, aged in nebula, borrowed by oceans, borrowed by lungs, returned to sky. The element's cosmic voyage is long yet cyclical, forging galaxies, shaping climates, hinting at life beyond Earth. It glows teal in nebulae, powers metal oxidations on Mars, and guards DNA under an ozone veil. As we turn inward to oxygen's role in living cells, carry this stellar history with you. Each breath is a handshake with ancient supernovae. Breathe in again calmly. Hold. Release. Let shoulders sink. In the hush that follows, star-forged oxygen waits patiently to fuel the next heartbeat and the dreams soon to come. Role in life. 4.1. Oxygen inside the human body. Feel the next inhalation slip through nostrils, past pharynx, down trachea, branching bronchi, and finally into the spongy alveoli. Within a heartbeat, tiny capillaries wrap each air sac like lace. Hemoglobin, a protein studded with 4 iron porphyrin rings, greets the arriving O2. When one oxygen molecule binds, it twists the iron atom ever so slightly out of the porphyrin plane, coaxing the next 3 sites to bind faster. This cooperative embrace lets red blood carry nearly 1 billion oxygen molecules in every cell. Cellular respiration. Delivered to tissues, oxygen slips across mitochondrial membranes into the electron transport chain. Their cytochrome oxidase accepts 4 electrons and 4 protons, then marries them with 1 O2 to form 2 water molecules. The energy released pumps protons across the inner membrane, building an electrochemical gradient. ATP synthase. Tiny rotary motors let protons swirl back, converting potential into ATP, the currency that makes muscles contract, neurons fire, and memories form. One adult at rest repackages roughly 70 kilograms of ATP daily, powered almost entirely by oxygen's pull. Reactive oxygen species and defense. Not every oxygen atom walks the orderly ATP path. A small fraction becomes superoxide or hydrogen peroxide, reactive oxygen species that can fray DNA or oxidize lipids. Cells police these radicals with superoxide dismutase, catalase, and glutathione peroxidase. Antioxidant shields evolved over billions of aerobic years. White blood cell phagosomes, however, weaponize the same radicals to puncture invading bacteria, proving oxygen can defend as fiercely as it sustains. Signaling molecule. Oxygen not only energizes, it informs. Specialized carotid body cells sense arterial O2. When levels dip, they spark a reflex that speeds breathing and heart rate. At the nuclear level, HF1-alpha, hypoxia-inducible factor, roams freely only when oxygen is scarce, activating genes that grow new blood vessels and increase red cell production. Climbers on Everest rely on this genetic whisper to adapt over weeks. Tumor cells hijack the same pathway to lure fresh capillaries. Clinical oxygen. Hospital pipelines deliver 94 to 98% oxygen to patients in respiratory distress. Hyperbaric chambers bathe divers with lingering nitrogen bubbles so that high-pressure O2 shrinks emboli and speeds healing of anaerobic infections. Yet excess oxygen under pressure can trigger seizures, a reminder that therapeutic windows must stay narrow. Oxygen nurtures best in moderation. Metabolic bookkeeping. At rest, an adult consumes roughly 250 milliliters of O2 per minute. During a sprint, that rate may climb 12-fold. Mitochondria meet demand by accelerating electron flow. Hemoglobin responds by releasing oxygen more readily as local pH drops and temperature rises. The Bohr effect. Intense exercise thus becomes a symphony of temperature, acidity, and oxygen affinity, orchestrated without conscious thought. Inhale 4 counts, hold 4, exhale 6. Inside, a billion hemoglobin wheels just turned, each releasing its payload into hungry cells, each returning to lungs for another round. 4.2. Oxygen across the greater biosphere. Shift perspective outward from single cells to forests, oceans, and microbe-draped stone. Photosynthesis, the planetary exhale. In chloroplasts of leaves and in the thylakoid membranes of cyanobacteria, the oxygen-evolving complex, a cluster of calcium and manganese ions, splits water under sunlight. 4 photons drive 4 electrons out of 2 water molecules. 4 protons enter chemical cues. 1 O2 bubbles free. This reaction is life's hinge. Without it, no breathable atmosphere, no ozone shield, no aerobic metabolism. Every second, photosynthesis releases about 10 quadrillion grams of O2 globally. Enough to refill the entire atmosphere in 3,000 years if not for equal and opposite sinks. Marine oxygen engine. Half of all oxygen arises from the sea. Prochlorococcus, a photosynthetic bacterium the size of a dust grain, populates the sunlit ocean surface by the 100 quadrillion. Each cell carries barely 200,000 chlorophyll molecules, yet taken together they outproduce rainforest canopies. Phytoplankton blooms paint satellite images swirls of aquamarine. When they die, sinking bodies ferry fixed carbon to deep water, sequestering it for centuries and leaving released oxygen behind. Plants and respiration. Even phototrophs consume oxygen at night. Trees inhale O2 and exhale CO2 through mitochondria in roots, stems, and leaves. Old-growth forests often stay carbon neutral, balancing daytime production with nighttime use. The real planetary oxygen surplus comes from carbon that escapes decay. Wood buried in anoxic bogs, plankton entombed in abyssal clays, carbonate shells locked in limestone. Burial over geologic time slowly tilts the balance toward atmospheric accumulation. Extreme aerobes and microaerobes. At a South African gold mine depths of 3 kilometers, Desulfuridus audaxviator survives with water radiolytically split by uranium into hydrogen and oxygen, proving photosynthesis is not the only oxygen source. Meanwhile, in marsh sediments, cable bacteria shuttle electron centimeters along protein wires so that distant cell ends can access trace O2 above mud even while bodies sit in anoxic zones. Life bends oxygen gradients in remarkable ways. Fire ecology. Lightning ignites savanna grass. Oxygen fuels flames that clear dead biomass and return nutrients to soil. Some pine cones rely on fire heat to open scales, releasing seeds into ash-enriched ground. Yet oxygen never climbs high enough to turn each spark into conflagration. Earth's 21% sweet spot allows fire to sculpt ecosystems without sterilizing continents. Nitrogenase versus oxygen. Roots of peas and clover host rhizobia that fix atmospheric nitrogen, but nitrogenase, the key enzyme, is poisoned by oxygen. Plants solve this with leg hemoglobin, a heme protein similar to animal hemoglobin, that buffers O2 at microlevels. Enough for respiration, not enough to kill the enzyme. Thus oxygen, indispensable for energy, is chaperoned lest it sabotage nutrient capture. Reactive oxygen in signaling webs. Plants wounded by chewing insects create bursts of superoxide that propagate leaf to leaf, alerting distant tissues to ramp chemical defenses. Fungal spores germinate only after sensing host-produced hydrogen peroxide. Even social amoebae release oxygen pulses that guide aggregation. Across life forms, reactive oxygen flips from menace to messenger depending on concentration and timing. Oxygen and evolution. Rising oxygen reshaped protein architecture. Early enzymes used iron-sulfur clusters that corroded in O2, driving invention of copper and heme-based catalysts. Multicellularity blossomed as diffusion limits eased. Large predators evolved when oxygen levels crossed 10%. Mass extinctions correlate with dips in atmospheric O2, while radiations follow rebounds, linking biological diversity to redox tides in geologic history. Global budget. Photosynthesis plus weathering of reduced gases minus respiration. Wildfire. Oxidative weathering equals near zero net change on human timescales. Yet anthropogenic forces nudge the ledger. Fossil fuel combustion draws down O2 by about 20 parts per million per decade. Tiny compared to 21% but measurable with precise sensors. Deforestation reduces photosynthetic supply, while fertilizer-driven algal blooms end in oxygen-free dead zones. Though current trends pose no immediate oxygen scarcity, they foreshadow intertwined planetary health metrics. Carbon rise, oxygen slip, biodiversity loss. Pause again. Inhale for 4 counts, hold, exhale for 6. Imagine oxygen atoms you just breathed once resting in a maple leaf, then rusting an iron nail, then floating in the stratosphere protecting skin from ultraviolet. Oxygen fuels every fluttering sparrow, colors coral sand, etches ancient mountains, and silently records climate swings in polar ice. It is both sword and salve, energizer, oxidizer, messenger, and sculptor. In the next block we will harness this power, exploring cryogenic rockets, steel furnaces, hyperbaric chambers, and ozone sanitation. For now, rest in the certainty that each unhurried breath replenishes the flame of life in billions of cells. Breathe once more. Feel the rib cage widen like sunrise over tide pools. Hold. Release and sense warmth drift outward, joining an atmosphere shaped by cyanobacteria, guarded by ozone, and lit at night by green auroras. Oxygen remains at your side, quiet as snowfall, vital as heartbeat, patient as starlight. Practical applications. 5.1 Medicine. Picture a pre-dawn ward washed in soft amber light. Monitors blink green tracers. A quiet hiss escapes from a wall port marked O2. In this moment, oxygen is neither philosophy nor starlight, but an ordinary prescription measured in liters per minute. Supplemental breath. When pneumonia stiffens alveoli or asthma narrows bronchi, pulse oximeters drop below 94%. Nurses attach nasal cannulas or simple masks. Fresh gas streams at 2 to 15 liters per minute, raising arterial saturation, easing the myocardium's workload, and clearing the cloud of carbon dioxide from drowsy neurons. Millions of patients each year gain precious hours while antibiotics, bronchodilators, or surgery address deeper causes. High flow and mechanical ventilation. Intensive care units employ heated high-flow systems that deliver 60-liter rivers of humidified oxygen, flushing anatomical dead space and matching inspiratory demand. Should lungs fail outright, ventilators cycle volumes at set pressures, blending oxygen to precise fractions. Respiratory therapists titrate that fraction because too little invites hypoxia yet too much breeds oxidative stress. Hyperbaric therapy. Descend in imagination to a steel cylinder that seals with submarine weight. Inside, pressure multiplies to 2 or 3 atmospheres. Patients breathe 100% oxygen through hoods. Under those conditions, plasma alone carries ample O2 to perfuse tissues starved by carbon monoxide poisoning, diabetic foot ulcers, radiation necrosis, or decompression sickness. At depth, gas bubbles shrink, angiogenesis accelerates, and anaerobic bacteria lose footing. Surgical theaters and anesthesia. Anesthesiologists blend oxygen with nitrous oxide or sevoflurane vapors, maintaining end-tidal O2 for brain protection while volatile agents keep consciousness at bay. Modern machines check each breath. Alarms ring if fraction dipped. Surgeons wield electrocautery wands that would spark wildfire without the hospital's strict 40% ceiling in the circuit. Neonatal life. Premature lungs lack surfactant. Alveoli collapse like damp tissue. Incubators supply warmed air laced with 32% oxygen and continuous positive airway pressure. Within hours, fragile chests regain rhythm. Yet neonatal staff shield eyes from excess. Too much oxygen scars retinal vessels, a lesson learnt painfully in the 1950s epidemic of retinopathy of prematurity. Liquid oxygen at home. Chronic obstructive pulmonary disease patients wheel silver dewars through hallways. Inside, -183-degree oxygen slumbers as blue liquid. A simple valve vaporizes it, feeding lightweight nasal tubing so grandparents may climb steps or garden in dusklight without drowning in carbon dioxide. Advanced imaging and diagnostics. MRI magnets glean contrast from hemoglobin's magnetic flip between oxygenated diamagnetism and deoxygenated paramagnetism, mapping neuronal activation in functional scans. Positron emission tomography employs O15 water, half-life 2 minutes, to trace cerebral blood flow. Though the radionuclide vanishes in a coffee break, the image of thought it prints can guide tumor resections with millimeter confidence. Inhale 4 counts, hold 4, exhale 6. Consider how every clinical advance ultimately rests on oxygen's willingness to slip into plasma, hide in hemoglobin, or glow in radiotracer arcs, all while remaining the same simple element. 5.2 Technology and heavy industry. Leave the ward, don a hard hat, and step into a plant where orange steel streams like lava behind protective glass. Here oxygen performs alchemy at city scale. Basic oxygen furnace. Molten pig iron royals in a refractory vessel. From above, a water-cooled lance injects 95% oxygen at supersonic speed. Silicon, manganese, carbon, and phosphorus oxidize in minutes, raising temperature and purging impurities. The carbon monoxide plume escapes, sometimes burnt for power, sometimes trapped in gas holders. The basic oxygen process replaced open hearth furnaces, slashing conversion time from 8 hours to 40 minutes and enabling the skyscraper era. Oxy-fuel cutting and welding. Fabricators attach a preheat flame of acetylene, then trigger a high-pressure oxygen jet. The iron-rich edge ignites exothermically, slicing beams with clean kerfs. Welders flip the principle, mixing oxygen with acetylene to melt filler rod and fuse joints. No other gas matches oxygen's oxidizing fervor. Propane and propylene work, but iron melts slower, edges roughen, costs rise. Rocketry. High above factory roofs, launch pads suspend silver tanks of liquid oxygen nicknamed LOX. In Saturn V they breathed with RP-1 kerosene. In Space Shuttle main engines with liquid hydrogen. The stoichiometric plume of hydrogen-oxygen exhaust is mostly steam at 3000 Kelvin, hotter than melting steel yet environmentally benign. Starship prototypes chill steel skin with autogenous gaseous oxygen during ascent, proving oxidizer can be structure and coolant as well as flame. Pulp and paper bleaching. Soon after logs macerate into lignin-laden pulp, oxygen delignification reduces chlorine demand by 70%. Pressurized O2 dissolves into alkaline slurry, generating peroxide in situ that lifts color bodies. White pages emerge, rivers remain clearer, and chlorine-induced dioxins shrink to whispers. Glass and wastewater treatment. Replacing air with 85% oxygen in glass furnaces raises flame temperature, yet cuts nitrogen oxide emissions. Municipal plants bubble pure oxygen into activated sludge tanks. Microbes devour sewage faster, reactors shrink, odors fade. Semiconductor fabrication. Thin films of silicon dioxide grown in dry oxygen furnaces form the gate dielectrics of microchips. Every phone call, text, or late-night lullaby streaming service rests ultimately on atomic layers birthed when oxygen diffused into glowing silicon wafers. Chemical synthesis and green oxidations. Hydrogen peroxide factories start by reacting anthraquinone with oxygen under pressure. Epoxy resins polymerize after peracetic acid, made by combining acetic acid with hydrogen peroxide from oxygen, adds oxygen across carbon double bonds. Catalytic aerobic oxidations using gold or palladium now replace chromium. 6. Reagents, cutting toxic waste. The dream of using molecular oxygen as sole oxidant drives research in biomimetic catalysts patterned after copper oxidases in fungi. Energy storage. Metal air batteries couple aluminium, zinc, or lithium anodes with ambient oxygen cathodes. During discharge, oxygen reduces to hydroxide, freeing electrons to light LEDs or drive motors. Lithium-air prototypes promise energy densities approaching gasoline, though cathode clogging and recharge inefficiency remain barriers in pilot labs. Take another breath. Hear distant furnace roar morph into quiet household hum. Both run on oxygen's appetite for electrons, scaled from ton to whisper yet ruled by identical thermodynamics. 5.3. Everyday life and familiar comforts. Return from steelworks to kitchens, gardens, and sidewalks where oxygen accompanies without fanfare. Cooking in flame. A blue gas hob flame owes its color to complete combustion in oxygen-rich swirl ports. In wood-fired ovens, flame tips lick oxygen at arch peaks, browning pizza crust with Maillard aromas. Outdoor charcoal grills depend on adjustable dampers. Starve oxygen and coals smolder. Flood it and steaks char to ash. Candles and celebration. Paraffin melts, wicks draw fuel upward, and capillary action balances with oxygen diffusion to sustain yellow flame. Birthday cakes, vigils, power-cut lanterns. All stand on that simple diffusion flame where wax vapor meets ambient O2. Beverages and freshness. Winemakers flush tanks with nitrogen first, then top barrels with low-pressure oxygen to mature flavors slowly. Brewers inject precise micro-oxygen bubbles post-fermentation to let yeast finish ester balances. Cold brew coffee sealed against oxygen tastes chocolatey weeks later. Unprotected it sours in days. Food preservation. Modified atmosphere packaging blends 70% nitrogen, 30% carbon dioxide, and trace oxygen to keep lettuce emerald and salmon coral. Oxygen absorbers. Sachets of iron filings. In dried fruit pouches scavenge residual O2, arresting rancid fat oxidation. Gardening and soil. Earthworms churn loam, dragging oxygen down burrows so aerobic microbes can mineralize nutrients. Overwatered houseplants drown when roots cannot access oxygenated pore spaces. Porous potting mix revives them by reintroducing gaseous pathways. Aquaria and ponds. Air stones cascade fine bubbles, raising dissolved oxygen for goldfish and angelfish. Ice anglers cut breathing holes in frozen lakes. Without exchange, fish suffer winterkill when photosynthesis halts under snow-muted light. Sports and adventure. Mountaineers clip aluminium bottles to harnesses. At 8,000 meters, each breath through a regulator feels like 2 at sea level. Pilots of unpressurized aircraft don oxygen masks above 12,000 feet, forestalling hypoxia's euphoria that masks danger. Scuba divers carry 95% oxygen cylinders for emergency decompression stops. Pure O2 accelerates inert gas washout. Wellness trends. Oxygen bars bubble scented O2 through water, promising clarity though benefits rarely exceed placebo. Athletes deploy portable concentrators in live low train high regimens, sleeping in hypoxic tents to stimulate erythropoietin, then breathing rich oxygen before sprints. Cleaning and stain removal. So-called oxygen bleaches combine sodium percarbonate with warm water, releasing hydrogen peroxide that oxidizes wine spills without chlorine odor. Carpet cleaners aerosolize similar solutions. Bubbles lift soil and vanish into harmless oxygen and water. Fire safety. Self-contained breathing apparatus for firefighters store compressed air, not pure oxygen, to avoid flare-up, but the principle remains. Deliver O2 shielded from smoke. Spacecraft cabins maintain 21% O2 at reduced pressure to cut risk of high-pressure leaks. Art and culture. Glass blowers feed oxypropane torches to shape swan-neck vases. Jewelry makers chase colors on titanium by heating with micro-oxygen flames, coaxing oxide layers that refract peacock blues and purples. Oxygen renders pigment and patina, craft and cuisine. Pause for a final breath cycle. Notice how many daily comforts, crispy crust, reading lamp, morning jog, lean on invisible partnerships with oxygen. From life support to launchpad, from sourdough tank to nebula electronics, oxygen labors everywhere. It can sear steel, heal tissue, bleach pulp, and kindle birthday wishes. Its versatility springs from unwavering hunger for electrons, a hunger civilization channels into art, flight, flavor, and health. Let that thought settle. Inhale 4, hold, exhale 6. Sense oxygen sweeping through alveoli, ironworks, rocket nozzles, and rose gardens in one vast planetary breath. As we drift toward curiosities and mysteries, carry the image of oxygen as both torch and bomb, an element equally at home in ICU and nebula, blast furnace and backyard firefly night. Breathe softly. The practical wonder continues with every candle lit, every steel beam lifted skyward, every heart quietly beating in the dark. Curiosities and Mysteries. 6.1. Fascinating or surprising facts. Liquid oxygen is naturally sky blue. Most liquids tint only when soluble pigments intrude, yet condensed oxygen shows a gentle aquamarine hue all its own. The color comes from weak, spin-forbidden electronic transitions. Quantum whispers usually muffled in molecules with paired electrons. When troop medics poured chilled oxygen into doers during the Second World War, many paused, transfixed by that improbable glacier tone swirling under field tents lit by kerosene lamps. Oxygen makes flames dance in microgravity. A match on Earth pulls teardrop-shaped as warm gases rise and fresh air rushes in. In orbit, heat has no buoyancy. Experiments aboard the International Space Station show spherical flames, blue and ghost-like, fed by slow diffusion of oxygen. Astronauts call them flame marbles. Their quiet burn teaches engineers how to design safer cabins and smarter fire suppressants for future lunar bases. Green comets reveal oxygen in disguise. Old sky guides warn that comets glow green where tails join heads. That glow is oxygen, but not in the familiar O2 or O3 forms. Sunlight breaks water into atomic oxygen. Excited O superscript 1 powers a forbidden transition at 557 nanometers. The same eerie green colors auroras. Whenever a green comet flares, observers unknowingly watch ultraviolet carved oxygen from an ancient ice storehouse. The smell after a lightning strike. That sharp metallic scent drifting through storm fresh air is ozone O3. Each bolt pumps 300 million volts into humid sky, splitting O2. Recombining atoms form ozone and nitrogen oxides, the first step in natural fertilizer. A nose can detect ozone at 10 parts per billion, proof that our ancestors evolved to sense the subtle oxidative warning in storm air. Glow stick chemistry comes from oxygen's cousins. Crack a glow stick and diphenyl oxalate reacts with hydrogen peroxide, releasing peroxyacid that excites a fluorescent dye. The peroxide is made industrially by autoxidation of isopropyl alcohol with molecular oxygen. So a child's summer nightlight flickers thanks to oxygen harvested from industrial air separators. Paramagnetic levitation of droplets. Physicists at Leiden University floated millimeter droplets of liquid oxygen between the poles of a laboratory magnet. Visitors watched blue beads hover, wobble, and spin like alien marbles. The demonstration showed that diamagnetic graphite escapes the field while paramagnetic oxygen embraces it, a gentle reminder that quantum spin can overcome gravity on a tabletop. Inhale 4, hold, exhale 6. Notice how every mundane breath hides wonders. Blue droplets defying magnets, green comets whispering through vacuum, flame spheres floating in silence. 6.2. Unresolved mysteries or unusual phenomena. The faint young sun paradox. Stellar models say the young sun glowed 25% dimmer than today. Such a weak star should have left oceans frozen. Geological evidence, though, shows liquid water and early life. One solution invokes reduced greenhouse gases balanced by lower oxygen. Another suggests high CO2 and methane offset faint sunlight, later trimmed when oxygenic photosynthesis rose. The precise interplay between early oxygen levels, greenhouse chemistry, and solar output remains uncertain. Why Earth's oxygen held steady for 600 million years. After the Neo-Proterozoic oxygenation event, atmospheric O2 stabilized near present values despite mass extinction fires, supercontinent breakups, and volcanic outpourings. Feedback loops involving phosphorus burial, sulfur weathering, and wildfire frequency are proposed, yet climate models still struggle to hold oxygen within 20 to 30% for hundreds of millions of years. Somewhere, a stabilizing gear in the biogeochemical engine remains hidden. Peroxide snow on Europa. Spectral readings detect hydrogen peroxide across Europa's surface, generated as charged particles from Jupiter's smash water ice. How deeply peroxide penetrates, and whether subsurface ocean currents bring it to potential microbial habitats below the crust is unknown. Even trace delivery could fuel simple metabolisms. Future landers will sample brittle ice shards to hunt this oxidant. High-pressure oxygen crystals beyond imagination. Crush oxygen above 90 gigapascals, 900,000 times surface pressure, and the simple diatomic gas polymerizes into opaque, reddish solids. Some high-pressure phases show superconductivity, others behave like semiconductors. Researchers squeeze microdroplets between diamond anvils, fire lasers, and watch Raman spectra shift, but cannot yet stabilize these phases at ambient conditions. Unlocking polymeric oxygen could yield new electronic materials or ultra-high-energy oxidizers. Oxygen on Venus nightside. Orbiters have spotted green line emissions high above Venus's dark hemisphere, signaling oxygen atoms recombining. Where does atomic oxygen arise on a planet whose dense carbon dioxide atmosphere screens most ultraviolet? Hypotheses include dayside photolysis followed by subsolar circulation, or sulfur photochemistry in sulfuric acid clouds. Pinning down this nightside oxygen engine will improve climate models for terrestrial exoplanets with thick atmospheres. The Great Oxidation Trigger. What sparked cyanobacteria to proliferate and tip atmospheric oxygen past the 1% threshold 2.4 billion years ago? Some geologists cite tectonic upthrust of nutrient-rich shelves. Others propose evolution of cellular mechanisms to detoxify oxygen, allowing cyanobacteria to expand. Direct fossil evidence is sparse. Noble gas isotopes in ancient shale nodules hint at spikes of hydrogen escape to space, suggesting interplay between oxygen, methane, and hydrogen loss. The definitive trigger remains elusive. Pause again, release air slowly. Feel the curiosity oxygen stirs, still a puzzle piece shy of complete, beckoning nighttime thinkers. 6.3 Little-known aspects and historical anecdotes. Oxygen balloons at Georgian fairs. In 1785, a London chemist demonstrated Priestley's dephlogisticated air by filling silk balloons. Spectators paid a shilling to inhale, reporting lofty sensations and a bright, brisk taste. Fashionable diaries record ladies fainting from delight beneath oxygen canopies. The fad subsided after a faulty valve burst, startling a carriage team into bolting down Fleet Street. The chalk cliffs that built cathedrals. Every block of French limestone carved into Gothic arches began as the shell of a marine plankton called coccolithophore. During Cretaceous seas, these organisms captured atmospheric CO2 via photosynthesis, released oxygen, died, and rained skeletal plates onto seabeds. Compressed into chalk, they later rose in tectonic swells. Thus the nave of Notre Dame stands on ancient plankton breath. Green fire of Verdun. During the First World War, French medics noticed wounded soldiers manifesting vivid emerald flames as antiseptic powder ignited phosphorus on uniforms saturated with pure oxygen from field cylinders. Photographs show flickering green against night trenches. The eerie light sped adoption of safer sodium hypochlorite irrigation in forward medical posts. The first glass of oxygenated beer. In 1936, a Czech brewer bubbled pure oxygen through lager to accelerate conditioning. The beer matured overnight, but oxygen staled hop aromas within days. Patrons praised its clarity yet complained of papery flavors by week's end. The experiment proved instructive. Oxygen is brewer's ally in yeast growth but enemy in finished product. Apollo's pure oxygen cabins. Early Apollo spacecraft operated at 1/3 atmospheric pressure but 100% oxygen. The setup cut launch mass but led to tragedy when a wiring spark ignited cabin materials during a ground test of Apollo 1. Afterwards, designers retreated to nitrogen-oxygen mixes during ground operations, venting to pure O2 only after reaching orbit, underscoring oxygen's double-edged brilliance. Ink that breathes. 19th-century stamp forgers discovered that exposing old iron gall ink documents to moist oxygen revitalized faded browns into fresh blacks, easing overstamping of false signatures. Museums now store manuscripts in low-oxygen vaults to slow the same oxidative darkening, preserving original tones. Oxygen snow on Antarctica's high plateau. At Dome A, winter temperatures plunge below -90 degrees Celsius. Satellite spectrometers suggest heavy supersaturation of water vapor and carbon dioxide near surface. Theoretical work predicts transient precipitates of solid oxygen microflakes at -183 degrees. Scientists hunt such flakes with cryogenic filters, hoping to confirm a snowfall invisible to naked eyes. Fill lungs slowly once more. Imagine each inhaled molecule as a witness to wonders. Lightning's perfume, cometary glow, whispering superconductors under diamond pressure. Oxygen does not parade. It surprises, sometimes lurking where theory falters, sometimes revealing itself in emerald burns or teal droplets. Exhale and picture that departing breath climbing through ceiling beams, slipping into night air, perhaps bound for a thundercloud, a leaf, or the bloodstream of a night-flying bat. Mysteries travel with it, unfinished, waiting for dawn laboratories or starlit contemplations. Rest now in the spaciousness those mysteries create. There is room to dream precisely because oxygen's story is not finished. In the hush between heartbeats, curiosity and calm breathe together, ready for the final descent into sleep where imagination may unwrap the next secret of the element that keeps life alight. Elemental Dreams and Sleep Descent. 7.1. Gathering calm images of oxygen. Let your body find its preferred stillness. Shoulders sink toward mattress. Arms rest where gravity places them. Draw a single deliberate breath through the nose. 1, 2, 3, 4. Pause for 4, release for 6. As air leaves, Imagine the room quieting by a notch, like a lantern wick turned lower but burning steadier. Now close the theater curtain of the eyelids and allow a picture to project on the inner screen. A misty dawn lake. Water lies mirror flat, tinted blush rose by climbing sun. Above the surface floats a silvery haze, each droplet a tiny chamber holding dissolved oxygen that escaped cool water overnight. Dragonflies skim, their wings tracing ripples of barely audible taps. Listen to one of those ripples travel outward, meeting others, then fading into calm. With every outward circle the mind eases. A second image rises, a forest clearing at midday, shafts of sunlight slanting through oak canopy. Dust motes dance where light strikes, and each mote carries a cargo of oxygen exhaled by leaves minutes ago. Watch a mote drift toward you. It floats in front of the nose, and as you inhale the mote dissolves into breath, merging with bloodstream, joining millions of its kin already at work. There is no sensation, only knowledge that the forest's generosity just entered the pulse. Shift now to night. Above open grasslands a green auroral ribbon undulates from horizon to zenith. The color glows from oxygen atoms 100 kilometers high, recombining after dayside sunlight tore them apart. Slow wave-like folds travel across sky as if the magnetosphere is breathing, in for a minute, out for a minute. Imagine synchronizing chest rise with auroral swell, chest fall with its quiet retreat. Each pulse feels slower than the last. One final image appears. A single candle flickering on a bedside table. Surrounding the flame is a still glass hurricane lamp. Oxygen slips through vents at the base, feeds the wick, and departs as gentle upward heat. The flame bows when you exhale and straightens when you inhale, in perfect dialogue. Breath fuels flame, flame signals calm. Hold that conversation in mind. Silent, steady, unhurried. Notice how the body has softened further. Jaw unclenches. Muscles behind eyes release. Breathing finds its own cadence. Time feels less like marching seconds, more like a wide, slow current. 7.2. Weaving oxygen into the rhythm of sleep. Begin a quiet mantra that rides each breath. Inhale. Pure. Exhale. Quiet. No voice needed. Let the words form like thoughts of water droplets on glass, present yet weightless. Repeat for 3 cycles, then allow the syllables to fade, leaving only their relaxed imprint on rhythm. Turn awareness inward to the bloodstream's corridor. Visualize scarlet riverways branching finer and finer until they become shimmering capillary threads. Red cells drift, each carrying 4 oxygen parcels. Watch one cell squeeze through a capillary so narrow it folds like a soft pillow, surrendering oxygen packets to waiting muscle fibers. The fibers accept, quick convert to energy, then relax deeper. See thousands of cells performing the same dance, a ballet choreographed without your direction, continuing effortlessly through sleep. Shift to the brain's twilight galleries. Neurons slow their chatter as adenosine levels peak. Oxygen uptake declines a fraction, signaling that it is safe to enter night's repair mode. Astrocytes clear metabolic byproducts, microglia patrol synapses, all powered by fewer yet sufficient oxygen whispers. The mind glides from active thought to passive sensation, like a bird folding wings to drift on warm currents. Move focus to the surface of skin. Tiny vessels called papillary loops deliver warm, oxygenated plasma just beneath epidermis, releasing subtle heat that meets cool room air. The gradient forms a microclimate, a thin, invisible shawl that insulates without fabric. Feel that warmth especially at fingertips and toes, warming the edges of consciousness. Return to breathing. The diaphragm now rises in half-speed waves. Each inhale collects exactly what body requests. No surplus, no scarcity. Each exhale carries away gentle carbon dioxide, which nudges brainstem to time the next inhale, a call and response older than language. Now imagine a wheel of day and night. On the lighted half, photosynthesis splits water, liberating oxygen. On the dark half, respiration reunites oxygen with carbon, releasing warmth that rises in night air. Your own cycle echoes planetary rhythm: daytime energy, nighttime rest. The wheel turns beneath you, but you feel no jolt, only a faint rocking like a boat moored on calm bay water. Deepen relaxation with a countdown linked to breaths. Inhale. 5. Exhale. Quiet. Inhale. 4. Exhale. Quiet. Continue down to 0 at your pace. Notice each number arrive slower than the one before. By 2, eyelids feel heavier than satin curtains. At 1, thoughts blur like chalk lines in drizzle. When 0 drifts by, numbers dissolve entirely, leaving simply the feeling of floating. If stray wakefulness sparks, perhaps a creak of floorboard or flash of memory, picture dipping that spark into a pool of liquid oxygen. A soft hiss, an instant chill, the spark shrinks to harmless bead of frost, sinks beneath surface, gone. The pool seals again, calm and blue. 7.3. Drifting into oxygen's endless cycle of rest. See yourself now in a gondola beneath a high-altitude balloon. The balloon's envelope holds warmed, oxygen-rich air. There is no engine, only gentle lift. Landscape recedes until rivers look like silver laces, woods like ink blots. Higher still, the stratosphere fades to indigo. Above, a slender ozone veil glimmers, absorbing stray ultraviolet so that your voyage remains safe. The gondola rocks slightly, synchronized with breathing swell. Inside the gondola stands a silver flask. Open it and blue vapor drifts, supplying pure, chilled oxygen. You close the lid. There is no need for extra. Lungs feel full, heart unhurried. You settle onto a cushioned bench. The wicker floor creaks softly, an ancient lullaby of woven cane. Through the window you spot auroral ribbons far north, hydrogen-pink fringes blending with oxygen-green arcs. They pulse like giant phosphorescent hearts, reminding that magnetic fields and oxygen atoms dance far above weather. The balloon drifts closer until green light spills onto your lap, painting skin mint cool. The glow does not dazzle. It soothes like slow harp notes. Gradually the scene dims. The aurora recedes. Balloon descends through padded cloud. Each cloud bank muffles more sound until silence reigns. No wind, no engine, only heartbeat and breath. Balloon touches down in a meadow bathed in silver moonlight. You step onto grass that springs gently, releasing petrichor hint of rain. Around, thousands of night-blooming flowers open, each exhaling faint oxygen after moonlit photosynthesis. Their scent is soft, like linen dried in dawn sun. You lie on the grass. Above, Orion tips westward, belt stars crisp in cool air. With every inhalation, oxygen from flowers joins cosmic oxygen from nebulae, merges with breaths of forest owls, travels into your bronchioles. Exhalations join night breeze heading toward distant oceans. The whole planet participates in this exchange. You float at its center, neither pushing nor pulling, simply drifting. At last the boundary between breath awareness and sleep softens. Inhalations shorten, exhalations lengthen, then lengthen again, until brainstem decides to automate breathing without waking mind. This moment is the doorway. Step through. Dreams may gather elements just explored. Misty lakes, candle flames, stratospheric auroras, silver balloons, night flowers. They may rearrange them into gentle narratives where oxygen glows as guide. Or dreams may empty entirely, leaving restful black velvet. Either way, oxygen stands sentinel, ensuring myocardium beats, synapses restore, tissues knit. Take one final conscious breath, cool, buoyant, sustaining. Hold softly, sensing ribcage expand 1 small centimeter. Release. Muscles yield, jaw slackens, Eyes drift below REM threshold. Breathing continues, independent, rhythmic, secure. Night deepens. The element of life hums all around. In crickets singing nearby, in roots exchanging gases with soil, in tides dissolving coral sand. You belong inside that hum, safe and quiet, carried like a leaf on oxygen's endless current. Sleep now. Oxygen will keep watch. Now, as our journey softly comes to a close, allow yourself a moment of quiet reflection. Feel how each calm breath gently connects you to the element we've explored tonight, one tiny piece in the infinite mosaic of the universe. As you drift gently toward rest, picture your thoughts like atoms of the element we've visited today, floating serenely through the vastness of your imagination. Just as elements combine, transform, and quietly support all life around us, your mind now settles, combining peace with tranquility. Remember how every atom within you once journeyed through stars, oceans, and forests, cycling endlessly through the great natural symphony. Tonight's element, in its silent and humble way, is part of that eternal flow, gently sustaining the heartbeat of existence itself. Think of the wonder we share. This quiet exploration, this peaceful communion with matter. With each soft exhalation, you return the element back into the embrace of the world around you, an invisible yet profound exchange. You are part of this endless rhythm, connected in every silent moment, every restful sigh. Imagine the element we've discovered tonight, existing beyond time, beyond human stories, gently present long before us, and quietly continuing long after. It carries the memory of ancient worlds and dreams of futures yet unseen. You too hold this gentle eternity within each breath. Allow yourself now to float gently, as if carried by the element's invisible hands, toward restful sleep. Feel comforted by knowing that the universe generously shares every atom, every molecule, every peaceful moment with you. Let your eyelids grow heavy, your thoughts softly dissolve like mist at dawn. Know deeply that you belong, gently cradled in the elemental harmony of the cosmos. May your dreams tonight be filled with quiet wonder and peaceful exploration. Rest now, knowing you are safe, cherished, and connected to this gentle element, to this gentle earth, and to the vast, beautiful silence of the universe itself. Good night, and rest peacefully, embraced by the elemental calm of night chemistry.